Welcome back. And now we are going to talk about finding the tangent line to a level curve. So thinking about a topographic map. And remember how we observed when we looked at this picture in previous video that the stream flows perpendicular to these contours or these level curves. Okay. So since the downflowing stream is going to reach its destination in the fastest way, it must flow in the steepest direction down, which is going to be the direction or the magnitude of the negative of that gradient vector for the directional derivative, right? So, and we learned about that in the previous video. That was our second property. The function decreases most rapidly in the direction of the opposite or the negative of the gradient of f for the directional derivative. Whew. That's a mouthful. But the main thing is we're perpendicular. So thinking about it this way, we need to recognize when we're finding these equations for tangent lines to level curves, they are going to be normal or perpendicular to the gradient. So we'll think about it this way. The line through a point, P naught, which is normal non-zero vector, we'll call it n, which is non-zero, is some quantity a, I, plus b, j. And that would have the equation a times x minus x naught plus b times y minus y naught equals 0. And if n is the gradient, if n equals, we'll say, the gradient of f evaluated at that point, which would mean we have the partial of f at that point, plus the partial of y at that point. As long as this is not the zero vector, then this equation gives us the formula for the tangent vector. So really what we've said is that normal vector is the gradient, okay? Because remember that normal vector, the gradient, is the way that we're traveling most rapidly, either increasing or decreasing along these curves. So the tangent is parallel to the curve, right? And so that gradient and the tangent are perpendicular. That's why we're using n for normal. Anyhow, this leads us, and combined with this guy, this leads us to the formula for the equation for a tangent line to a level curve. So we can see that here. Partial of the function with respect to x at the point, x minus x naught, plus the partial of y at the point, times y minus y naught, and that needs to equal 0. So let's do an example using this formula. In this equation, we're given an ellipse, and we're going to find the equation for the tangent line on that ellipse at this point, -2, 1. So essentially what we're thinking about here is the ellipse, this one singular ellipse, is representing a level curve, okay? So it's a level curve. I can't write and talk today. It's a level curve of the function. So maybe we have some function z being a function f of xy equals x squared over 4 plus y squared. So we're looking at this one level curve where z is equal to 2. So in order to work this problem, we are going to need to find the gradient. And we can work with it as long as the gradient is not 0. So the gradient of f at -2, 1, the given point, is the partial of x, so that would be 2x or 1/2 x times I, plus the partial of the function with respect to y, so 2y j, evaluated at -2, 1. So plugging in -2, I've got -1. Plugging in that 1, I get 2. So I have negative I plus 2j, and we're in luck because it's not the 0 vector. So since this is not 0, we can write the equation of the tangent line. And the equation of my tangent line is the partial of the function with respect to x at that point, -2, 1, times x minus that -2 value, plus the partial of y at that point, -2, 1, y minus that y value, which is 1, equal to 0. So my partial of x is right there. I just need to evaluate it. And my partial of y, 2y. So plugging -2, 1, and we really aren't plugging in the 1, but -2, 1 into this, I get out -1. So I have -1, x minus -2, which is going to be plus 2, plus, putting my -2, 1 in here, I've got positive 2. And then I've got y minus that positive 1 equals 0. So simplifying, -x minus 2 plus 2y minus 2 equals 0. -x plus 2y equals 4. 2y equals x plus 4, or rather y is 1/2 x plus 2. So this is the equation of the tangent line to that level curve, which is on my surface. And I've got a picture to help you visualize, and we'll connect that parallel versus, or tangent versus perpendicular situation. So what I have here is my elliptical level curve. So this ellipse is just one of many potentially curves, and we're just looking at where z is equal to 2. And so on that level curve, here's my gradient. My gradient is directly perpendicular to the curve, and then my tangent line is touching right there. The tangent line is perpendicular to the gradient. So that is, to reiterate what we just did, that's how we find the tangent line to a level curve. Now, since we kind of understand what a gradient is and how to find it, I do want to ensure that we know how to work with it. And so just want to illustrate that we have many algebraic rules for gradients. And basically this is just saying that, we know that these operations, the sum, if we have the gradient of some sum, the gradient for f plus g, well, that's just the gradient for f plus the gradient of g. I should say the gradient of f plus the gradient of g. So the gradient of the difference of two functions would be the gradient of f minus the gradient of g. So the gradient of a difference is the difference of the gradients. If we have a constant, we can pull that constant k in front of the gradient. And then if we are dealing with the gradient of a product or the gradient of a quotient of functions, then we would say f gradient g plus g gradient of f, or g gradient of f minus f gradient g divided by g squared. And so these, you should notice, they look like our product and quotient rules for derivatives. So they're very similar to the corresponding rules for the derivatives of single variable functions. And I would be remiss if I didn't show you an example of just using these properties to simplify. So we'll do two quick examples just illustrating how these algebraic properties or these rules apply to gradients. Here we are given two multivariable functions, f and g, and each has their corresponding gradient. So for example, if we wanted to find the gradient of f minus g, and these are really simple functions and the gradients are correspondingly simple, but sometimes that difference could be really messy. So this is just a tool we could use to kind of simplify our calculations. But by definition, this would be gradient of f minus gradient of g, which is I minus j minus 3j. I do want to note that you would need to make sure to distribute that negative. We only have one term here, so this is going to simplify to I minus 4j. And this is just a very simplistic calculation to show you that we can use these algebraic properties on gradients. We could be given much more complex functions that have much more complex gradients, and using this strategy of breaking it into two pieces then could allow for an easier calculation in the future. Similarly, we will do example B, where we find the gradient of the product of f times g. So again, if I could view that function that I was trying to find the gradient of as a product of two smaller functions, then this could be useful for me to solve this. So really, we are doing a more conceptual problem here. But by definition, we'll have f times the gradient of g plus g times the gradient of f. I can't scroll that out of the way. F is x minus y. The gradient of g is 3j. G is 3y, and then we have that times the gradient of I. So simplifying this, I have 3xj minus 3y j plus 3y I minus 3y j. So combining my i's and j's, well, I only have one I, so I have 3y I plus my j coefficients are 3x minus 3y minus 3y. So I've got 3x minus 6y j. Okay, so this is just, to let you know of the concept of how we could use these gradient operations, these algebraic operations on gradients to simplify an expression or to potentially simplify our calculations. So just to summarize, we did two things in this video. We talked about finding the tangent line to some level curve on a surface or of a surface. And then we also talked about, now that we are doing calculations with gradients, we have these algebraic properties that we could use to potentially simplify calculations. All right, have fun, be safe. Good luck.